So this one is alkene. The very first reaction in alkene is electrophilic addition. Electrophilic addition. What is electrophilic addition? Let me tell you. Electrophilic means electrophile. Addition means add. So alkene attacks on electrophile first. So if you look at this HX, if you look at the HX group, X means halogen, which can be chlorine, bromine, and iodine. So this is delta negative, this is delta positive, because X is a electronegative in nature. So this would be my electrophile because of positively charged. So double bond is going to attack on the H part, means proton, like this. And this hydrogen halogen bond is going to break towards X because X is more electronegative. This alkene is symmetrical because left and right is exactly same. So you can generate carbocation on any of the carbon, either left or right. Suppose carbocation in the left side here. Then hydrogen must be on the other part of the carbon here. Make sense? So this is my intermediate, which is called carbocation. So in electrophilic addition, carbocation is intermediate. And whenever you have a carbocation as an intermediate, always check the rearrangement. Rearrangement. This is already stable carbocation, so no need to rearrange. And in the next step, Br minus is my nucleophile and it is going to attack over the positive charge. So you have this product, bromine here. Make sense about the electrophilic addition reaction. So two things in electrophilic addition. First, generation of carbocation, and second, nucleophile attacks over the carbocation. Make sense? Please tell me, everyone. You can write down on chat box. It makes sense? Okay. Suppose we have this alkene. And here we have HBr. So let me tell you how we can proceed this one. So again, alkene double bond is going to attack over H and this Br bond is going to break. So now we have to generate a carbocation, and you have two positions where you can generate a carbocation, either this carbon or this carbon. Clear? So you can write down like this one and this one. Let me know which one is more stable, one or two. Yes, one is more stable. So we will use this carbocation. So alkene protonate with the H and it forms a more stable carbocation, this one. Now this is secondary carbocation. Now I have another question. Is there any possibility of rearrangement in this case? Yes or no? Rearrangement, yes or no? Rearrangement means less stable form to more stable form. So if you have a secondary carbocation and you have a chance to make it tertiary, then that means there is a rearrangement. And yes, here we have a hydrogen. This carbon have a hydrogen. So this hydrogen is going to shift over the positive charge and we have a tertiary carbocation, this one. And this is called 1,2 hydride shift. Hydride shift. Once we have the most stable carbocation, in the next step, very easy. Br is my nucleophile. It would attack on the most stable carbocation and it would be the final product. Make sense? Perfect. I have a question for you. what would be the product? Options are which one? A, B, C, or D? Okay, look at here. This alkene is going to attack over this proton and this bond is going to break. So we have this carbocation. This is secondary carbocation at this moment. And here we have a hydrogen. And now there is a rearrangement because we have the most stable carbocation at tertiary position. So this one is the most stable one. And in the next step, iodine minus is going to attack over the most stable carbocation. So this would be the final answer. Make sense? So C would be the right choice. If you still have a doubt about the rearrangement stability of carbocation, then please watch lecture 1 and lecture 2. For rearrangement, lecture 2. And it is reaction mechanism series. Reaction mechanism. Clear? I have already done so much about the rearrangement in SN1, in E1. So please watch that. Now this is a potential energy diagram for electrophilic addition reaction. You know that in electrophilic addition reaction we have two steps. First step, second step. First step is the formation of carbocation. Whenever we have a carbocation, that would always be a slow step. Slow step means high peak, and you can see the peak is high. So this is my generation of carbocation, which is a rate determining step, which means slow step. And second step is a fast step, the nucleophilic attack over the carbocation. And you can see the nucleophile attack in the second step, which is a fast step. And final product, we have this one. So this is a graph. And this is my intermediate. Now the very first reaction is hydrohalogenation. Hydrohalogenation means addition of hydrogen and halogen. So this is my alkene. This is HBr. We can say HBr means HBr like this. So alkene attack over this H. This bond is going to break. So now you can draw the carbocation. This one, the very first carbocation is this. And here we have two possible carbocation A and B. Let me know which one is more stable, A or B. Yes. So we will use this carbocation, and in the next step, Br minus is going to attack over this carbocation. So product would be this. Is this carbon is chiral? Please tell me. This carbon is chiral? Yes. Whenever we have a chiral center in product, then we have a chance to draw as a wedge as well as dash. Clear? So wedge and dash both. Make sense? So whenever you have hydrohalogenation reaction, it means addition of HBr, it means addition of HCl, it means addition of HI. These three are the most common one. And in this case, the reactant would always be alkene. So alkene is going to react with HBr, HCl, HI. So carbocation is my intermediate. And whenever you have a carbocation as an intermediate, there is a chance of rearrangement and then nucleophile attack on the most stable carbocation. Make sense? So the key point is rearrangement, key point is carbocation intermediate, and this kind of reaction is under the category of electrophilic addition reaction. Make sense? So this is the case of rearrangement. So you can see this alkene is going to protonate. So you have this carbocation. There is another carbocation if you want to draw like this. Out of these two, this one is a more stable, and here we have a hydrogen. So there is a chance of 1, 2 hydride shift. So this hydrogen is going to shift in the right side. So you have a tertiary carbocation and then Br attacks over here. So we have the final product. Make sense? Could you please tell me the name of this compound, this product name, IUPAC name? Sometimes it could be in your option. There is no drawing of the structure. It would be like the name of the compound. So could you please tell me the name of this compound? Anyone? What would be the name? First job is to identify the longest parent chain, the carbon chain, longest carbon chain. So 1, 2, 3, 4, or from this side 1, 2, 3, 4. So 4 carbon would be my longest carbon chain, and then start numbering from that end where the branch get the lowest. So 1, 2, 3, 4. Yes, 2 bromo, 2 methyl butane. Very good. Next is hydration reaction. Again, it is electrophilic addition. Hydration means addition of water. Water means H and OH. H generally have positive, OH generally have negative charge. So it's addition of H and OH. And again the same concept. Again the same concept. Carbocation would be my intermediate. And if you want to draw the mechanism, then it would be O plus H, H, H. Alkene is going to protonate this. So you have the most stable carbocation. And the next step, H2O, the nucleophile is going to attack. So O plus H and H. And in the next step, we still have H2O in the solution. So it is going to deprotonate the hydrogen. So overall you have OH like this. So in DAT, the simple thing is that it is an addition of OH group. Carbocation is intermediate. Rearrangement is possible. And the name of the reaction is electrophilic addition reaction. Make sense? Please tell me. So at this moment, we have covered two reactions, the hydrohalogenation and hydration, and both have carbocation as an intermediate. This is the rearrangement case, same as the hydrohalogenation. Again, there is a carbocation. This carbocation is unstable, so it can rearrange by hydride shift. So we have this one, the most stable, and then we can add OH at the most stable carbocation. Clear? Next, addition of alcohol. Again, same thing. Carbocation is intermediate, electrophilic addition. And in CH3OH, you have to add OCH3 group, CH3O minus as a nucleophile. Do not add OH. If you are familiar with the mechanism, then you know that in the last you have OCH3. So you can write down the mechanism in this way. It would protonate. So we have the carbocation, then hydride shift, and then alcohol is going to attack here. So O plus H and methyl group. We still have alcohol in the solution. So it is going to deprotonate this H. So finally you have OCH3 here. Make sense? So whenever you have addition of alcohol, always add OCH3. Means you can break like that. CH3OH means O minus and plus. So the nucleophilic part would be this. Clear? is the only in presence of acid. Yes, means this is addition of alcohol, so we can add in presence of yes, acid as well. You can carry out this reaction in presence of base as well. So base is going to deprotonate the alcohol. So we have CH3O minus as a nucleophile, and then it would attack. Clear? Next is Markovnikov's, very, very important concept. But I would like to add here, don't apply in case of rearrangement. I'll give you the example evidence for the rearrangement case as well. So Markovnikov's is negative part of nucleophile. Negative part of nucleophile attacks on carbon double bond carbon which has less number of H, less number of proton. So this is my double bond. This carbon have one hydrogen and this carbon have two hydrogen. So this carbon have less. So Br is my nucleophile. So it would attack over the less hydrogen containing carbon. In other words, you can say more substituted carbon as well. More substituted carbon. The negative part means nucleophile. So if you look at this double bond, this carbon is more substituted because more carbon over here. Makes sense? Both the words is very clear. Please tell me everyone. I would like to say always follow the less hydrogen containing carbon. And let me give you an example of rearrangement and without rearrangement. For example, suppose we have this alkene and we are going to use Markovnikov's over here. So if you are going to follow Markovnikov's rule, then your product would be this. Br should be here. Tell me everyone, it makes sense because this carbon have less hydrogen. Clear? So this is Markovnikov's product. You know that whenever alkene treated with HBr, so it is electrophilic addition. So carbocation is my intermediate and this carbocation is now going to rearrange. So this is the most stable and then Br attack over here. So the final product would be this. So it would be the final answer. This is wrong. Make sense? So do not apply Markovnikov's in case of rearrangement. Clear? Next, anti-Markovnikov's. The best way is, in case of anti-Markovnikov's, especially for alkene, always HBr with peroxide linkage, this kind of linkage. An example is like H2O2, ROOR, RC double bond OR, they all have peroxy bond. So whenever HBr with peroxide, it would be anti-Markovnikov's rule. And anti-Markovnikov's means just opposite of Markovnikov's, which means negative part of reagent attacks on that double bonded carbon, which is less substituted or more hydrogen containing carbon. So this carbon have more hydrogen. So Br would be here. So we have this one. Make sense?
Give them to them. That's why I need to ensure that they're leveraging these reports that show that in date. Okay. And
it makes sense. Please tell me. Okay, next is halogenation. Halogenation means addition of two bromine or two chlorine atom in anti side. and there is no rearrangement, and bromonium ion is an intermediate. So simple thing is, this is the double bond carbon. We have to add two bromine, and they must have opposite direction. It means one on the wedge, so one on the dash over the double bond carbon. For example, suppose we have this alkene. So if you are using Br2CCl4, how do we know when it is Markovnikov or anti-Markovnikov? Does it depend on the nucleophile? I have to. Okay, Markovnikovs means only HBr or HCl or HI. This is Markovnikovs. Anti-Markovnikovs means HBr with peroxide, HBr with H2O2 or ROR, any peroxide bond. So HBr is only the case here, not HI, no HF, no HCl. Make sense? So Br2CCl4 means both the bromines should be in anti side. So one on the, suppose one on the wedge and one on the dash like this. Clear? So this is called anti. Next, bromination in H2O. Here we have a carbon chain. This is methyl here. So Br2 with H2O. So it is again anti-addition of OH and Br. What does it mean anti-addition? Anti-addition means OH and Br have opposite direction. Opposite direction. You can see here Br on the wedge, so OH on the dash. Here OH on the wedge, so Br on the dash. Makes sense? That means anti. And H2O means the negative charge would be OH ion and it would attack on the more substituted carbon here and Br on the less. For example, suppose you have this alkene and we are using Br2 with H2O. So OH is going to attack on the more substituted carbon here and Br on the less. This makes sense? Please tell me everyone. It makes sense, bromination one? I am requesting to everyone. It makes sense? There would be no rearrangement. Clear? And what is bromonium ion intermediate? Let me tell you about it. Suppose you have alkene and here you have Br2. So this alkene is going to attack over here, it breaks. So you have a cyclic bromonium ion in this way. Br plus Br like this. So this is called bromonium ion, cyclic bromonium ion. Make sense? Next, bromination in alcohol. Same as H2O, same as water. But in alcohol, the nucleophile part would be OCS3 and it would attack on the more substituted carbon and Br on the less. You can see. And again they have opposite, means OCS3 on the wedge, Br on the dash. OCS3 on the dash, Br on the wedge. Anti-addition of Br and methoxide and Markovnikov's rule, bromonium ion is intermediate, there is no rearrangement. Make sense? This is very, very important reaction, oxymercuration and demercuration. In short, you can say OMDM. Oxymercuration, demercuration. So key point is, this is reagent combination. This is my reagent. And you can see there is a mercury. So you can memorize mercury means Hg, Hg means mercuration. Name reaction is mercuration. And here we have H2O. It means addition of H and OH. Overall, it is addition of H plus and OH and there would be no carbocation. Only Markovnikov's rule. So Markovnikov's is what? The negative part of nucleophile, which means OH ion, attacks on the carbon of the double bond on the carbon which has less number of hydrogens. So over here. So OH is going to attack over here. So you can see. Make sense? I said Markovnikov's. Markovnikov's means less hydrogen containing carbon or more substituted carbon. Clear? And the second thing, look at the trick here. Mercuration. Markovnikov's. So M stands for mercury and Markovnikov's. Markovnikov's. Clear? For example, we have suppose this one. And we are using this reaction OMDM. So what would be the product? OH attack on the carbon which has less number of hydrogen. So it would be here. Make sense? Please tell me everyone. Perfect. Similarly, alkoxymercuration. Alkoxymercuration means the nucleophile would be CH3OH, which means methoxide ion would be nucleophile. So it would attack on the carbon which has less hydrogen. Again the same. OCH3, OCH3. One thing I would like to tell you between oxymercuration, demercuration, and alkoxymercuration, the H2O one is more important. This one. So this one is more important. Alkoxymercuration is not important. Okay. But it's simple. Next is hydroboration oxidation. Very, very important reaction. In short, we can say HBO. And it is opposite of OMDM. Opposite of OMDM. Opposite means we know that OMDM is a Markovnikov's. So hydroboration oxidation is anti-Markovnikov's. And how can you memorize it is anti-Markovnikov's? Look at this H2O2. I told you peroxy linkage. And the simple thing is nucleophile is my OH minus. So it is again the same H plus and OH ion. So negative part would attack on the carbon which has more number of hydrogen. So this one have more number of hydrogen. So OH should be here. And this is syn addition. Syn means the H plus and OH ion both have same direction. So you can see OH on the dash, so hydrogen on the dash. OH on the wedge, so hydrogen on the wedge. Make sense? Please tell me. Any doubt? Next is isotopic effect of hydroboration oxidation. So H2O2 OH ion, this is my nucleophile. It would attack on the, according to anti-Markovnikov's, it would attack on the carbon which has more hydrogen. So here, so OH should be here. You can see. Do not memorize less or more substituted. I told you the technique. Whenever I am talking about Markovnikov's, it means less hydrogen containing carbon, less hydrogen containing carbon. And if I am talking about anti-Markovnikovs, then more hydrogen containing carbon. More hydrogen containing carbon. Easy. So look at this carbon double bond carbon. Here we have a hydrogen, but here we don't have any hydrogen. So this carbon have hydrogen, which means more hydrogen containing carbon. So anti-Markovnikov, so OH attack over here. Make sense? And BD3 here, we can use deuterium from BD3. Okay. So deuterium and OH. So addition of D and OH. So D is just isotope of proton. So it is D plus and OH minus. So we can add D and OH and they have syn addition. Clear? So that is called isotopic one. Next, syn dihydroxylation. Syn means same side. Di means two. Hydroxy is OH and ation means addition. So it is a addition of two OH group in the same side. Reagent is osmium tetraoxide. So both the OH you can see having same direction, either wedge or dash dash. Clear? This is common mistakes to avoid. So you can see this double bond carbon, and here we can have we used wedge on both the carbon, but there is no chiral center over here. You can see here we have two hydrogen. So this one is not chiral. Clear? So do not draw wedge and dash here. You can simply use plain bond because we don't have a chiral center. Clear? So we can add like this OH and either wedge OH or dash OH in the next one. Clear? We don't have a chiral center here, so you can use a plain OH. There is again another reagent for syn dihydroxylation, KMNO4 with OH ion. Again the same thing. So we have covered syn dihydroxylation two reagent. One is KMNO4 and second one is OSO4. The both means syn dihydroxylation. Clear? Please tell me, it makes sense? This is very, very important, anti-dihydroxylation. So anti means opposite. Opposite means both the OH have opposite direction. So one on the wedge, one on the dash. This is one is the wrong one. So you can correct this. One on the wedge, one on the dash, or one on the dash, one on the wedge. Clear? So anti means RCO3H with H3O plus hydrolysis. Next is epoxidation. What is epoxide? Epoxide is a three-member oxygen containing ring. Oxygen containing ring. And you can use the reagent RCO3H or MCPBA. MCPBA is called metachloroperbenzoic acid. Metachloroperbenzoic acid. But in DAT, it would always be in terms of MCPBA. MCPBA. Suppose we have this alkene and we are using MCPBA. So we can draw a three-membered oxygen containing ring over the double bond. Means insert oxygen like this. Simple. You can see this is my trans alkene. So epoxide would be here and both the carbon is anti to each other. So one on the wedge, one on the dash. If suppose we have cis alkene, then epoxide would be here and one on the wedge, this one also on the wedge, or dash dash. Makes sense? Please tell me it makes sense. Perfect. Next, catalytic hydrogenation. Hydrogenation means addition of hydrogen, and it is syn addition. Syn means both the hydrogen should be same side. You can see dash dash or wedge wedge. So double bond is reduced into single bond overall. For example, suppose we have this reaction alkene, and alkene is treated with H2PD. So this double bond would become single bond. And you know that it should be CH3, it should be CH3. For example, suppose you have this alkene and we are using H2PD. So overall, it's a simple alkane. Means we can reduce the double bond into single bond. Make sense? Ozonolysis. Ozonolysis is of two types, reducing and oxidizing. So in reducing, the combination is this one. Ozone with zinc H2O or dimethyl sulfide. And the best way to draw its product is break the double bond and add a double bond O on the carbons. So if you look at this side of the carbon chain, so you can see a double bond O. Plus look at this carbon, carbon, double bond O, and two more carbon. So here we have H as well if you balance. Make sense? Suppose we have the ring and we are doing reducing ozonolysis, means O3 zinc H2O. So you can use the numbering 1, 2, 3, 4, 5, 6. Break this one, add double bond O, double bond O. So now 1 and 6 bond is going to break. Suppose this is my 1. 1 have double bond O with H. 1 bonded to 2, 2 bonded to 3, 3 bonded to 4, 4 bonded to 5, 5 bonded to 6, double bond O H. Make sense? Please tell me, everyone. Perfect. Next, oxidizing condition. Oxidizing always have H2O2 or KMNO4 with hydrolysis. And whenever you have aldehyde as a product, it would oxidize to give carboxylic acid as a final answer. So this is oxidizing ozonolysis. For example, we can break this and double bond O, double bond O. So 1 mole should be this and 1 mole should be this. And you know that this is aldehyde. So aldehyde further oxidized to give acid. So add another O, this. So this one and this one would be the final answer. Make sense? You can see aldehyde oxidized to give carboxylic. Retroozonolysis, very, very important. Retroozonolysis means product to reactant. So this one is my product and we have to figure out the reactant. So simple thing is that combine both the oxygen and remove them and add the carbon-carbon bonds. So carbon, double bond, carbon. So this would be my reactant. Clear? Suppose we have this one. What would be my reactant? So write down both the component in such a way where you can represent both the oxygen approaching each other like this. Make sense? And you can cross check your answer. Break this, add double bond O, double bond O. So you can see. Clear? Make sense? Mechanism of hydrohalogenation we have done, alkene protonate, carbocation, Br attacks over the carbocation, and we have this product. Yes, we have this question. Would you like to try this? This is RCO3H with hydrolysis. This is anti-dihydroxylation. Anti-dihydroxylation. This is BS3THF H2O2. This is HBO, hydroboration oxidation. This is simple Br2 with CCl4. So this is anti-dihalogenation. This is normally hydrogenation, which means reduction of double bond into single bond like this. And this is Markovnikov's or carbocation, means electrophilic addition simply. So you can use this one, Br over here. And this is anti. So both the OH should be anti side. One on the wedge, one on the dash like this. And here THF, this is hydroboration oxidation, which means anti-Markovnikov's. Anti-Markovnikov's means OH attack on the carbon, which has more hydrogen. So here. Clear? Please tell me everyone, it makes sense? It makes sense? Yes. You can match your answers. Okay, this one is common mistake. This carbon is not chiral. So you can use a plain bond here. This is not wedge, only a plain bond. Okay. So it should be a plain bond. Clear? Rest is easy. Propose a mechanism. This is your homework. I can tell you this one. HBr, we have done a lot. Alkene attacks, it breaks. So we have this carbocation. Now it would rearrange into the most stable. So we have this one, and then Br attacks over here. Clear? And the product of this OH here. Makes sense? This is the most stable carbocation. Regioselective. Regioselective means this is alpha, this is beta 1, beta 2. I have done this in elimination reaction. Elimination. E1, E2. Elimination reaction means if you have two different alkene, you can see this is two different alkene. So most stable alkene would be major, means more substituted alkene would be major. You can see this is more substituted, 2 carbon. And here just 1 carbon chain. This is more substituted. More substituted. And this is less substituted. And they are structural isomer of each other. Structural isomer. So regioselectivity means whenever reactant have two product and they both are structural isomer of each other, so anyone can be major. It depend on the nature of the alkene. So more substituted would be the major here. So this is regioselective because they are constitutional isomer or structural isomer. Constitutional is also known as structural isomer of each other. What is stereoselective? Stereo means reactant have two product. Product 1 and product 2. And they both are stereoisomer of each other. Stereoisomer. And out of them, any of the isomeric form is more stable. You know that if you have this alkene, this is cis and this is trans. We know that trans form is more stable than cis. So that's why this is stereoselective. Make sense? Please tell me. It makes sense? So stereoselective means any of the stereo product is major. Regioselective means any of the constitutional isomeric product is more stable. And stereospecific means any special kind of stereoisomeric reactant can give a product. Like you know that in E2 elimination, it is anti-periplanar. Anti-periplanar. Anti-periplanar means alpha halogen and beta hydrogen must be anti to each other. Clear? You know that the hydrogen and beta, for example, suppose we have this bromine and here we have this hydrogen. So you know that this is anti to each other. Br and hydrogen is anti. So we can eliminate, and that is called stereospecific. All done? I would like to give you a homework. So we can use this slide. Last one. Let's use this one. HBr A, HBr with H2O2, B, Br2 CCl4, C, Br2 H2O, D, we can say OMDM. OMDM means oxymercuration, demercuration, or we can say HgOAc whole twice, NaBH4H2O. So this is E, B2H6H2O2, OH minus. This is HBO, hydroboration oxidation. Sometimes in place of B2H6, we have BH3. So this is F. Next, OSO4, G. Next, KMNO4, H. Next, O3 with zinc H2O, I. And the last, H2, PD, charcoal, J. Please take a picture of this. Yes, cold or heat. This is this is it's a sin dihydroxylation. Both. Oh, I missed one. MCPBA1. This is K. Clear? And in the next session, we will cover alkyne, free radical, Diels-Felder. Clear? Any doubt? Okay, thank you so much, everyone. Bye.